So last week we left off, actually, we did a calculation for an acid-base titration, which was good, exactly as far as we needed to get so that Monday lab could work on that. So Wednesday lab, you'll be doing that today, an acid-base titration. And we're going to go from there, and we're going to talk about strong acids, strong bases, kind of like introduce this topic. There really won't be any questions on it. So strong acids, well, hydrochloric acid is a strong acid. Hydrofluoric acid is not a strong acid. So even though they have very similar formulas, right, it's hydrogen and then chlorine, hydrogen and then fluorine. They're actually quite different based on how they behave in a solution. So a strong acid is one that completely ionizes in solution. And then a weak acid, like hydrofluoric acid, is a weak acid. Well, does not completely ionize, or you could say that it partially ionizes. And when I say ionize, that's kind of this reaction of the HF splitting apart into the H plus and the F minus ions. And so that's ionization. So we've got strong acids, we've got weak acids. Again, strong acids ionize completely. So when you put them into a solution, you're not going to have any of the original hydrogen and chlorine bound together anymore. It's all going to be separate hydrogen ions, separate chloride ions. So for a solution of hydrochloric acid, the concentration, if it's 1 molar hydrochloric acid, the concentration of H3O plus will also be 1 molar. Complete ionization, so you get the same number of hydrogens off of the chlorine as you have hydrochloric acid. And then this will be something that we talk about next week also. There's a single arrow here. So as a little precursor to what we're going to talk about in chapter 15 next week, a single arrow means that the reaction goes completely and none of it comes back and forms any of the reactants. Most reactions, though, there's some amount of these that, the H3O plus hits a chloride and they form the reactants again in a dynamic equilibrium. It doesn't really happen with strong acids. So these are electrolyte solutions, kind of like Pedialyte, has electrolytes in it. Gatorade has a lot of electrolytes. Those are these ionic compounds that completely solubilize in water and create ions. Those ions allow water to conduct electricity. So if you take pure water and you stick wires in one side and then have a wire come out the other side, don't do this at home. You need some other special equipment, not shown here, to make this safe. But if you don't have any electrolytes in the solution, then there's no way for the water to conduct electricity. Light bulb doesn't light up. If you have electrolytes in there, could be a hydrochloric acid solution, could be salt, sodium chloride, then those ions can actually ferry electrons back and forth between the two terminals. And then that can carry electricity, and so the light bulb lights up. There's a table here of some of the strong acids. Again, I'm not going to have you memorize this table. If anything, I would give you the table at the end of the thing and say which of these is a strong acid. Probably the most likely question I'll ask is I'll say, what is a strong acid? And then give you some of the properties of strong and weak acids, and it would be like a multiple choice question. So some of these here, well, most of these actually, hydrochloric acid, hydrobromic acid, hydroiodic acid, they all have a single hydrogen in the formula. And even nitric acid just has a single hydrogen. Oh, I missed this one too. Perchloric acid, also a single hydrogen. So those are monoprotic acids, right? Mono equals 1. So they only have a single ionizable proton. So it means that proton can come off and become that H plus ion. Sulfuric acid here is an example of a diprotic acid. So mono means 1, di means 2. That's an acid that has 2 ionizable protons. So you can get both of these protons off of here and create 2 H plus ions for every 1 sulfuric acid molecule. Weak acids, unlike strong acids, do not completely ionize. And in fact, most of it doesn't ionize. So there are very, very few ions in the solution. So it's those ions that allow the water to conduct electricity. So there aren't a lot of ions, but there's like a little bit, so it can conduct electricity weakly, or it can conduct electricity a little bit. The partial ionization that's happening here is because some of the hydrofluoric acid will react with water and lose its proton to become hydronium and a fluoride ion. But then also, fluoride will be like, actually, I want that hydrogen back, and it'll grab it from the hydronium and form water and hydrofluoric acid again. And it does that enough that there are only a few ions in solution. So again, pure water doesn't conduct electricity, but if we have a solution of hydrofluoric acid, we can get a weak light bulb. So it glows only dimly because only a little bit of the electricity is able to be conducted. You got a table of some weak acids here. There are a lot of them. A lot of them are carboxylic acids, which is an organic chemistry term. 2 of the weak acids here are diprotic. And one is triprotic. Sulfuric acid, was the diprotic strong acid that we saw. And actually with sulfuric acid, losing the first proton is a strong acid. Losing the second proton is a weak acid. So it doesn't lose all of that second acid. And that's the case actually for most polyprotic acids. So if they have more than one proton, they're kind of slow to lose any of them after the first. All right, so if a strong acid ionizes completely, meaning that you're not left with any of the original acid, and a weak acid only ionizes slightly, can you pick out which one of these is the weak acid? Got 1 vote for C. Does everybody agree? Does everybody agree on C? Is that the one it was meant to be? Sorry. So if we look at these, and it takes a little bit to like orient yourself with these pictures, but here we have our hydronium, so that's all the red and white ones, and then iodine is the purple one. So hydrogen here is also the little white balls. So we don't see any of these spheres, the purple spheres, with a white sphere. So that means it's ionized completely. So this is a strong acid. And then we can move to the middle one here where we've got nitrate and hydronium. So again, hydronium is going to be the red sphere with 3 white ones. And then nitrate is the blue sphere with 3 red ones. So if we wanted to find a nitric acid in solution, we'd be looking for a blue sphere with 3 red ones and a white one. And there aren't any here in the solution. So is it a strong acid or a weak acid? It's completely ionized. It's a strong acid.
So if it's completely ionized, that's an indicator that it's a
Strong
strong acid.
acid. Strong acids are also strong electrolytes. So it creates a lot of ions in the solution, conducts electricity, strong electrolyte, strong acid. This last one then, by process of elimination, we know this must be the weak acid. And I can make this bigger because it's almost harder to see on this one. And I think even this is maybe a little bit of a giveaway because we didn't see that on the others. I think this is formic acid. And so that's going to be, well, this is formate. So we got two red spheres that are the oxygens. The black one in the middle there is the carbon. It's got one white sphere, so just one hydrogen. And because this has a negative charge, we know that that's the conjugate base of the acid. And there's only one of them in here that's ionized. So this has become an ion. HCHO2 is not an ion, and that's almost all of them. So we have almost all of the acid still, and only one ion. So this is the weak acid. All right, let me go through these quickly as well. So we want to determine the H3O plus concentration. Remember that strong acids ionize completely, so their concentration of H3O plus is going to be the same as the concentration of the acid. If we have a weak acid, we know that those only partially ionize, and since we don't talk about the actual math, which I think is the Henderson-Hasselbalch equation, which is a fun name, we don't have the math to do that, to calculate exactly what the concentration would be. So we're just going to say that it's less than the concentration of the acid. And I'll give these to you because I don't expect you to memorize it. I'm not going to go back and try and find the chart. Okay, so if this is, again, our formic acid from the previous slide, so that's a weak acid, what is our concentration of H3O plus? If it's a weak acid. Anyone? Yes?
So concentration is
Concentration is molarity.
molarity. Okay.
Or molarity is a unit of concentration. So it's the amount of something per, in molarity, it's the amount of moles per liter of water.
I'm gonna take a guess. Is it 0.50? Was it like the same number? Because I know we talked.
It's okay. It's okay. This is good. This is good. This is why I ask questions, to gauge the understanding of the room. So it's not to make you feel bad if you get the question wrong. It's never to do that. So, sorry. So here it's a weak acid, so only partially ionizes. So maybe this will help, maybe. If we have HCHO2, well, it's water. And then we're going to get H3O plus CHO2 minus. So these are the ions that we would create if we add this weak acid to water. So if I said we add, well, okay. So this is a weak acid, so that means that only a little bit of it is actually going to undergo this forward reaction. So we're not going to have very many of the H3O plus. So in this case, because it's a weak acid, the concentration of H3O plus is going to be less than 0.50. We don't know exactly what it is. If you take more chemistry, you can calculate it. But for now, we're just going to say it's less than 0.50. So for hydroiodic acid, that is a strong acid. So what would our concentration of H3O plus be?
1.25.
Yeah, it completely ionizes. So all of the hydroiodic acid that we put into the solution will split apart into these ions. So if we start with 1.25 molar HI, after that's reacted and reached equilibrium, we'll have 1.25 molar H3O plus and 1.25 molar I minus. Okay, so for hydrofluoric acid, we have another weak acid. So what's the concentration of the H3O plus for that weak acid?
Would it be less?
Less than 0.75.
And we're saying it's less because it's a weak acid, right?
Yes.
Okay. And obviously when it's a strong, and that means it's ionized, and then so it would just be, well, like for B.
Mm-hmm. It'll be the same as the concentration of acid that you had. Okay. So, talk about acids, talk about bases. So we have strong bases. This is just a list of strong bases. All of the strong bases I think that we talk about in this class are going to be of this form. So it's going to be some metal plus OH minus. The number of OH minuses will depend on the charge of the metal. So, right, lithium's a metal, sodium, potassium, and then hydroxide. Strontium hydroxide, strontium has a 2 plus charge, so strontium hydroxide has 2 hydroxides. So unlike diprotic acids or the polyprotic acids where they like ionize one hydrogen at a time and each hydrogen gets harder to remove, strong bases that have 2 hydroxides, it all ionizes in one step. So if you add strontium hydroxide, you'll get twice as many hydroxide ions as you had strontium hydroxide formula units. It's just a little diagram. So this is what I'm saying, is when we add that sodium hydroxide into solution, here we would be adding like 3 of these, right? 3 of those. As soon as it hits the water, it's going to split into sodium and hydroxide. So all 3 of these, at least that are depicted, would split. And so we get, in a space-filling version of this, these are your sodiums and those are your hydroxides. So strong bases are a lot like strong acids. Weak bases are like weak acids. So the most common weak bases produce hydroxide ions by accepting a proton from water. So they form the hydroxide indirectly. For example here, we have aqueous boron, or B, aqueous B, which is generic for a weak base. It takes a hydrogen from water, which then forms OH minus. And so here, we talk about these weak bases. It's really, or for a lot of these weak bases, it's in terms of a Bronsted-Lowry definition of a base. So it's a proton acceptor. So you do end up with hydroxide in the solution, but that hydroxide comes from the water that's already there, losing a proton. And again here, similar thing. So ammonia takes 1 hydrogen from water to become NH4 plus, and then leaves a hydroxide behind. So again here we've got, how many are added there? It's 1, 2, 3, 4, 5. So we had 5 ammonia molecules. Only one of these ammonia molecules has actually picked up a hydrogen to produce 1 hydroxide. So unlike weak acids where it's just sort of partially ionizing, the ammonia just has a very weak ability to steal a proton from water. I won't bother won't bother naming all these. But a lot of these weak bases are compounds that have hydrogen in them. And instead hydrogen, that ends up picking up the proton. So we got that, in pyridine, nitrogen picks up a proton to make that positive charge and creates hydroxide behind it. All right, so the same rules here. The same rules for strong acids, weak acids apply for strong bases and weak bases. So barium hydroxide is going to be a strong base. So what is the concentration of OH minus ions that would be formed?
Zero.
0.055. So it's the same. Oh, I'm sorry. Close. It's 0.055 times 2 because barium hydroxide has 2 hydroxides. Yeah. So it's actually 0.110 molar. Any guesses on whether this is a strong base or a weak base? All of the strong bases have hydroxide in them.
Strong.
Does it have hydroxide in it? Weak. It's a weak base because it doesn't have hydroxide. It just has a nitrogen. So what's our concentration of OH minus going to be in the solution?
Less than.
Oops, OH minus. So this is going to be less than 1.05. So sodium hydroxide is strong base or weak base? Strong base. Strong. So the concentration would be
0.45.
0.45. Because this one only has, sodium hydroxide only has 1 hydroxide. So this is equal to that. The other one is less than.
So like for H, since there was 2, that's why we chose it.
Mm-hmm.
So if there was like a different number, we would times by that.
Mm-hmm.
Wait, for H, wouldn't it be more than?
You mean, well, that's why we multiplied it. I wrote it down wrong the first time, but we multiplied it by 2 now. Yeah. So the first time I did do it wrong.
So it's a weak base when it has sodium, or it does not have.
Yeah, it does not. If it does not have hydroxide, and then you know it's a base, it's going to be a weak base. You'd have to also know that it's a base because, yeah. Don't worry too much about that. Okay, so, it's on the next slide. So water is amphoteric, which is a word we word I mentioned before, earlier in this chapter. So it can act like either an acid or a base. We've seen this happen a few times, right? When we have a weak base, it's where the nitrogen, like ammonia, steals a hydrogen. There, the water acts like an acid. But when we add an acid to water, that hydrogen goes and finds a water, an H2O, makes an H3O plus, and makes an acid, so that makes water a base. In pure water, water will react with itself in a process called self-ionization. So one of these water molecules will act as an acid, the other one acts as a base, and you end up with H3O plus and OH minus, even if they are in really tiny quantities. But there's always some H3O plus, there's always some OH minus in water. So we found this meme for this. Oh, you can't see. This is Thanos after they find him and he's destroyed the Infinity Gauntlet. He's like, I used the Infinity Gauntlet to destroy the Infinity Gauntlet. He says, I used the water to destroy the water. So water reacting with itself to make H3O plus and OH minus. I'll have to lighten that up so it shows up on a projector. You can kind of see it. All right, so it only occurs a tiny bit, but it's always there in any water. And so what happens is you end up with these small concentrations, but equal concentrations of H3O plus and OH minus, right? Because you have to destroy one water, or one water has to take a hydrogen from another water to get the H3O plus and the OH minus. So the concentration in pure water at 25 degrees C, because it does change with temperature, H3O plus and OH minus will be 1 times 10 to the negative 7 molar. So it's 1 times 10 to the negative 7 moles per liter. It's a very, very small amount. And we'll talk about equilibrium constants in the next chapter. But this ion product constant is an equilibrium constant. And when you take the concentration of H3O plus, multiply it by the concentration of OH minus, you get 1 times 10 to the negative 14. So that's a constant for water. So when it's neutral, they're both 1 times 10 to the negative 7. And then, actually here, I wanted to mention too that a trick with exponents, so if you multiply two exponents, or two numbers with exponents together, you just add their exponents. So we have times 10 to the minus 7 multiplied by times 10 to the minus 7. So minus 7 plus minus 7 is minus 14. So for a neutral solution, both the concentrations of H3O plus and OH minus is times 10 to the minus 7. In an acidic solution, you have a greater concentration of H3O plus than you do of OH minus. So this is when we add an acid to a solution, it ionizes, creates more protons, and increases the concentration of H3O plus. In a basic solution, OH minus, or hydroxide, is in a greater concentration than H3O plus. So this will be either with the weak acids that we talked about, where they're stealing hydrogens from water to create OH minus, increases that concentration, makes it more basic. Or we can just straight up add hydroxides to the solution and increase that hydroxide concentration. But regardless of whether or not we increase one or decrease the other, they always multiply together to equal this 1 times 10 to the minus 14. Because to increase the concentration of one, you have to destroy some of the other. It's kind of like a teeter-totter or an old school balance. Oh, this shows up okay. So because they always multiply together to equal the same thing, there's an interdependence between these two concentrations. So this is a scale here where we've got the H3O plus concentration on top and the OH minus, or hydroxide concentration, on the bottom. And remember, negative exponent, the larger the negative exponent, the smaller the concentration, the smaller the number. So if we increase the H3O plus concentration to, let's say, 10 to the minus 5, we have to decrease our OH minus concentration by the same amount. So going from 7 and 7 down to 5 and 7, now we've got 10 to the minus 5, and then 10 to the minus 9 for our OH minus concentration. And if we multiply those together, so 10 to the minus 5 times 10 to the minus 9, that equals 10 to the minus 14. So you'll find if you move anywhere on the scale, multiplying the H3O plus concentration by the OH minus concentration will always give you 10 to the 14, minus 14, negative 14. All right. So if we want to calculate the H3O plus concentration, we'll just use that relationship, which was the ionization constant of water, which is Kw, is equal to H3O plus multiplied by OH minus. So if we want to find 1, then we can just divide Kw, which is 10 to the minus 14. Yeah, let's do it this way. So we'll divide times 10 to the 14 by the hydroxide concentration to get H3O plus concentration. So for this first one, it'll be 1.5 times 10 to the minus 2 molar divided by, sorry. This will be 10 to the negative 14 on top over 1.5 times 10 to the minus 2. And that'll give us the H3O plus concentration. So 10 raised to the minus 14 divided by 1.5 times 10 to the negative 2 gives us a concentration of 6.67 times 10 to the minus 13. And that's molar H3O plus. So which concentration is bigger? Is it the OH minus concentration or the H3O plus concentration? The bigger the negative, if it's raised to a negative exponent, if that's a bigger negative exponent, then it's smaller. It's really hard to say. Yeah, so here, the 1.5 times 10 to the minus 2 is a bigger number. So if we have more hydroxide than we have acid, or H plus, is that acidic or basic? H plus is acid, OH minus is base. So if we have more base than acid, it's a basic solution. And we can go back to this other chart too. So this would be basic. And if we go back over here, we can see, so our OH minus concentration was 1 times 10 to the negative 2. And this will be a little bit rough because we're in between here. So that's a basic solution because our concentration here of OH minus is larger. Okay, so for this next one, we can do exactly the same thing. 10 raised to the 14 divided by 1.0 times 10 to the negative 7. And actually, I can do that one in my head. So it'll be 1 times 10 to the negative 7. So is the concentration of OH minus larger, or is the concentration of H plus larger, H3O plus? Or are they the same? They're the same. So if the concentrations are the same, then we don't have more acid, we don't have more base, so it's a neutral solution. And for this last one, again, 10 to the negative 14 over 8.2 times 10 to the negative 10. And that's going to be 1.2 times 10 to the negative 5. Yeah. So acidic or basic? Yeah, it's acidic because this concentration of H3O plus is larger. I think acids and bases are kind of funny because the hardest part is grappling with all of the new terms and all the numbers. But the math here is not complicated, right? We divide 10 to the minus 14 by the concentration of one of them, and it gives us the concentration of the other. And then getting used to looking at negative exponents and but really all we're doing is saying, is one concentration larger than the other? If the base is the larger concentration, it's basic. If the acid's the larger concentration, it's acid or acidic. So a scale that's easier to understand than saying times 10 to the negative whatever over and over and over again and trying to wrap your head around negative exponents is the pH scale. You're probably familiar with pH. You get you get pH balanced water, or you can get pH 8 water, I think is popular. Sometimes it's called alkaline. Whoops. Alkaline water. Alkaline essentially means basic, but only slightly. So on the pH scale, now if we have a pH of less than 7, it's an acidic solution. If the pH is larger than 7, it's a basic solution. And if the pH is equal to 7, it's a neutral solution. So pH is a measure of concentration. And we've basically taken that 1 times 10 to the negative 7, 1 times 10 to the negative 5, and we've transformed it so that it's easier to work with. We use a log function to do this. So the log function basically takes numbers and compresses the distance between them. So, for example here, if we have a pH of 4, that represents times 10 to the negative 4 molar H3O+. So this is our times 10 to the negative 4. If we go from a pH of 4 to a pH of 3, now it's 10 to the negative 3, which is not just sort of 1 unit larger, it's 10 times larger, because we changed this number by an exponent of 1, or by 1 exponent, which means that we're multiplying it by 10. We're not dividing it by 10. So then going from 3 to 2, now we've got 100 times larger than a pH of 4. So moving 1 unit on the pH scale is 10 times larger concentration or 10 times smaller concentration for every unit. Okay, explain logarithms. Logarithms are, I think they're just difficult to understand. They're easy to use, easy to type into your calculator. And one of the things I have to mention first is that your calculator probably has either one button that does two things. So like if you have the 36X Pro, if you press the log button once, it gives you ln. ln is the natural log. And then on the calculator, log, so if you press that button twice, is the log base 10. And we need the log base 10. If you use ln, you'll get the wrong answers for these pH problems. Okay, so what is a logarithm? So let's say that we have, let's say we have 10 raised to the 2. What is 10 raised to the 2? 10 times 10, so 100. All right, so what the logarithm is the logarithm is the reverse of this. The logarithm says, well, it solves this problem. So 10 to the what equals 100. So this would be, right, x equals 2. Written out as a logarithm, this would be log base 10, log base 10 of 100 equals 2. So when we're using this for pH, we're working with relatively small concentrations. We're working with small numbers. So if this is 10 to the negative 7, that's going to equal 0.1234561. That'll equal that, because that's 1 times 10 to the negative 7. So then the logarithm, log base 10, I keep doing the equals, of 0.0000, let's see, and that equals negative 7. So 10 raised to the negative 7 would give us that number. So the reason that for pH that we use the negative log is so that our numbers come out positive. Let me move this. So if we wanted the, let's say we want the pH of a concentration of 1 times 10 to the negative 3, H3O plus. So here, what is the pH of that? All you have to do is say negative log of 1 times 10 to the negative 3. Type that into your calculator, and when you hit enter, it will give you 3. It gets, so when the number, the coefficient there, when this is 1 times 10 to the negative 3, there's a 1 here, you can do those easy, because the negative log is always going to be whatever the exponent is. If this is something other than 1, then it gets a little bit, then you can't do it in your head. You have to type into the calculator, because it'll give you some decimal exponent that you have to multiply by. Your questions about logarithms? Okay. Helpful to know how they work. All right, so if we want to calculate the pH of each solution and indicate whether it's acidic or basic, we have 9.5 times 10 to the negative 9. To calculate pH, we say negative log of 9.5 times 10 to the negative 9 and the pH is 8.0. There's a bunch of decimals there, of course, but with the correct sig figs, it's just 8.0. So if you do the reverse, you're not going to get quite the answer that you started with because of significant figures here. But we'll get to how to reverse this, how to go the other way. All right, so for this next one, and we'll come back to whether it's acidic or basic. All right, so it's the negative log of 6.1 times 10 to the negative 3. Oops. So it's going to be 2.2 pH. So for the first one, is it acidic or basic? If the pH is, yeah. If it's higher than 7, it's basic. It's okay, we just learned it. So this is basic. Because again, this is the one place where the exponents get a little bit weird, because now we've gone from negative to positive. So if we wanted to reverse this and say what's that concentration in molarity, it would be 10 to the negative 8. So for this next one, acidic or basic? Acidic. So pH is less than 7, it's acidic. Cool. All right, so if you want to go the other direction, then we just raise 10 to the negative pH. So let's do the 8.0. So if we have a pH 8.0, and we want to get the concentration and molarity, then we would say 10 to the negative 8.0 equals, well, I mean, it's going to equal 1 times 10 to the negative 8. Let's do another number here. Well, which one do I want to say about this? So this is the reason that you need to know how logarithms work, to know that you're just raising 10 to the whatever, and that gives you the concentration from the pH. Because we're going to have some examples. I thought we had more examples. All right, I'll do another one here. So let me do this. So from that previous problem, right, so this was 9.5 times 10 to the negative 9. Because we rounded here, we lost some of that information. So the full number there, if we do pH of 8.02227639.5, to use all of the numbers that my calculator spit at me, we do, again, 10 raised to the 8.02227639.5. So that and negative, sorry, it's a negative. Oh, come on, calculator, you can do better. There we go. So now I get, this is 9.49 repeating times 10 to the negative 9. So if we were to use the two sig figs again, we would be left with 9.5 times 10 to the negative 9. But even with all of those digits, this still didn't quite give me back the exact number that I started with. So pH is a place where rounding error can affect your number a lot. So we'll do another one. So if we want to calculate the concentration of an H3O plus solution with a pH of 8.37. So 10 raised to the negative pH equals concentration of H3O plus. So 10 raised to the negative 8.37 will give us 4.27 times 10 to the negative 9. And that's always going to give you your concentration back in molarity, or moles per liter. So hopefully it's not too confusing. There's kind of just two equations here that you plug the numbers into. But that's why I made that worksheet that has, I think it has 60 problems on it. But it's all just negative log of whatever the number is equals. And then you write down the pH. And then it's 10 to the negative pH to give you the H3O plus. So basically just want to, incentivize that a little bit, and then it's just muscle memory training. Like just do it enough times, and you get the feel for it. And if you're handy with Excel, you can do it in like 30 seconds. Don't do it with Excel. It's cheating. You'll get all the right answers, but you can't use Excel on the test. Okay, so we've talked about pH now. I had another meme about POH. POH doesn't get talked about a lot, but it's a valid way to measure the concentration of acid or base. Well, measure the concentration of a base in a solution. So if you remember, we had that equation for this autoionization of water, H3O plus, OH minus. So we can take this, we can actually derive a relationship between pH and POH. So Kw is 1 times 10 to the negative 14 equals, right, whatever our concentration of H3O plus is times our concentration of OH minus. So we can do the exact same thing that we do for pH here, and we'll just take the negative log of both sides. So negative log of 1 times 10 to the negative 14. I'll write the step in. Negative log 1 times 10 to the negative 14. And then the negative log of these two things multiplied together. So on the left side, we can calculate that. So that'll be 14. So 14 equals, and one of the tricks of logarithms, if you're taking the log of two things being multiplied together, that's the same as the log of the first thing plus the log of the second thing. So we're going to leave this, negative on the outside there. This will be the log of H3O plus the log of OH minus. So POH is the log of OH minus. pH is the log of H3O plus. So we can substitute those out. We can say that this is now do I want the negative there? Oh, yeah. Sorry, I should have back up a step here. I'll do it on this step. So we're going to distribute that negative because it's the negative log that's pH. So negative log H3O plus minus the log of OH minus. So negative log of H3O plus concentration is pH. So we get 14 equals pH plus the negative log of OH minus concentration is POH. So that gives us the relationship between pH and POH. So if you have the pH, we can say 14 minus pH equals POH. And 14 minus POH gives us pH. I've said those words enough, those words enough now that they've completely lost meaning to me. They sound funny. But that's the relationship between POH and pH. So really, the same equations that we just did for pH are the same for POH. Negative log gives us POH. 10 raised to the negative POH will give us OH minus concentration. So if we want to calculate the OH minus concentration for a solution with a POH of 4.25, just like we did, so 10 raised to the negative POH is OH minus concentration. So 10 raised to the negative 4.25 equals 5.6, one more sig fig, 62 times 10 to the negative 5. Bonus question, is that acidic or basic? So POH is the opposite of pH. So it's basic. So lots of practice available on that worksheet. And it has the key. It's 2 pages, so the first page is all the questions, second page is the key. So you can know if you did it right. If you've been doing this along with me and you've typed stuff into your calculator and you get a different answer, just come talk to me afterwards, and we'll figure out the right buttons you need to press. Okay, so very quickly, buffers are a special situation when you end up with significant amounts, so a lot of a weak acid and its conjugate base. So a lot of weak acid, a lot of conjugate base, and essentially it acts as a buffer. In the whole sense of the word buffer. But if you add acid to the solution, that gets neutralized by the weak base. If you add base to the solution, it gets neutralized by the weak acid. So anything that you do that might change the pH of the solution gets countered by the high concentration of weak acid or its conjugate base. Human blood is a buffer. It's actually, so I never took a college bio class, somehow got away with that. I did take biochem though, and the buffer in your blood is carbonate, which we get from, well, cellular respiration produces CO2. When CO2 is dissolved in water, it forms carbonate. And so you need a certain amount of that in your blood to act as a buffer. So one of the places where that can go wrong is diabetic ketoacidosis, where your blood becomes acidified. So that pH drops outside of this healthy range and causes a whole host of problems. And if it gets too low, you'll die. So that carbonate, that CO2 that our lungs are always trying to get rid of, they get rid of it at a specific rate because we need enough of it around to counter any instantaneous changes to our blood pH. So one buffer system would be acetic acid and sodium acetate. So again, remember, acid is a proton donor. So we got a proton here to donate. And then on the other side here, we have its conjugate base. So if we add base to an acetic acid buffer solution, that gets absorbed by that acid. We make water, and then we make more of the conjugate base. So there's a limit to that, because if you use up all of the acid in the solution, that's when the pH actually starts to change. On the other side, if we'll have our significant amount of conjugate base, add acid to that solution, that gets neutralized, and it forms the conjugate acid and a salt. So the amount of hydronium, H3O plus in the solution, doesn't change significantly. So the pH doesn't change. Right, so the acid consumes any base, and the conjugate base consumes any added acid. All right, so which of the following is a buffer solution? Before diving that into right away, the requirements for a buffer solution is that it needs to be a weak acid / base, and you need to have the conjugate acid and base. So it needs to be a weak acid or base, and you need to have both the acid and its conjugate base, or base and conjugate acid. So if you don't have those two things, you can't have a buffer system. All right. So for A, H2SO4, sulfuric acid, what's wrong with this one? It's not a buffer system, but why? There's two reasons why it's not a buffer system. So we have SO3 and SO4. So they can't be conjugates. They can't be a conjugate acid, conjugate base of each other. That's one reason. Actually, I think there's three reasons here. So one, no conjugate. No conjugate base specifically, because these are both acids. So the second one I would call out would be that I think they're both. I think sulfurous acid is a strong acid. Sulfuric acid, though, is a strong acid. So it's definitely not going to be a buffer system because, reason that it's not is that it's a strong acid. And then the other thing is that both of these things are acids. So it can't be a buffer system if you only have acid. You just have an acid solution. So not a buffer. What about B? Is it a weak acid or weak base? I guess I can give that one to you because we just kind of covered those, and I don't expect you to memorize them. So hydrofluoric acid is a weak acid. So we do have a weak acid. So I don't know, check. Do we have the conjugate base? Yeah. Sodium fluoride would be the conjugate base. So this is, yes. Yes, buffer. How about C? Is hydrochloric acid a strong acid or a weak acid? Strong acid, yeah. So it's a strong acid. So that kind of disqualifies us right away. So no. It's a strong acid. We do, though, have the conjugate base of that strong acid. Doesn't count for much because it's a strong acid. I should say not a buffer. And what about this last one for D? Yeah, so it's a hydroxide base, so it's a strong base. So it's not a buffer because it's not a weak acid. It's not buffer, it's weaker. Sorry. Yeah, so it's not because it's a strong base. And then sodium chloride is not a conjugate. Well, actually, it would be the conjugate base of hydrochloric acid, but it doesn't form a conjugate system with sodium hydroxide. Yeah.
I have a question on B. So
Uh-huh.
I know that we determined that it does have a conjugate base. Would the conjugate base would it be the NaF or the HF?
It would be, well, which one's an acid?
HF is an acid.
HF is the acid.
So the conjugate base is, what's like the definition of a conjugate base?
Textbook definition of a conjugate base.
Like how would you know that that is the conjugate base? Like identify it.
So this is what I would point to. So if we have hydrofluoric acid, because it's an ionic compound, so sodium fluoride would be ionic. So in solution, you're going to get Na plus F minus. And then hydrofluoric acid, right? That with water would give you H plus and F minus. So it's the conjugate base because you have this F minus ion. So when hydrofluoric acid loses that proton, becomes F minus. So the sodium here is not important to the fact that it's a conjugate base. It's just the fact that in water that would make F minus. So it's if it's a like struggling with how to put this specifically into words. This is the last slide, so we can spend some time on this. But okay, so if this is an acid, I think this is where I'm tripping, because this is an acid. This is the conjugate base.
Got it. So just like identify the acid, and then if it's not the acid, then that's the conjugate base.
Right, but we could also write this reaction the other direction. So now here is F minus, an acid or a base. It's a base, because it's a donor proton acceptor. So now this is the base, and this is the conjugate acid. So the direction of the reaction is important. So this would be together a conjugate acid-base pair, because which one is the conjugate acid, which one's the conjugate base, depends on which way the reaction's going. So here we just identified that the first one was the acid, so we'll call the other one the conjugate base. But you have the pair of them, right? They'll always come in pairs.
So the bases are always the acceptors, right? Because
Mhm.
the F, the fluorine is accepting, so it's no longer negative, right? Because it becomes HF. No, that's the acid. HF is the acid.
Well, it becomes the acid.
Yeah,
Yeah, so it's the fact that it accepts this proton.
got it.
Yeah, so that's the Bronsted-Lowry definition of a base. It's a proton acceptor. And then a proton donor is an acid.